Let's talk about an exciting topic, the meaning of derivatives. What does it mean when you take the derivative of a function? Derivatives. So what we're going to do is we're going to draw three graphs. And we're going to compare the graphs. So say you're a biologist and you're observing wildlife and you're watching an animal swimming in a canal, and you notice that the animal is swimming at a constant rate. So you draw the graph and the graph looks something like this. So for every unit, let's make sure we have our axis labeled. So for every unit of time, the animal travels 1 unit of distance. So it's a straight line that you've drawn, and the formula would be distance d of t equals mt. Just basically describing a straight line. So notice that the rate is not changing. The rate remains constant. So in the next graph, we'd like to describe we're starting with the distance, the relationship between distance and time. We're going to talk about the speed. So as you've studied in physics, you know, speed is basically how the distance is changing. It's the change in the distance over time. So the speed, the formula for the speed is going to be st equals, and in this case, we noticed in our first graph that it's a constant. So it is a constant. So how do we draw that? We would draw it as a straight line. So notice that the speed is not going up, it's not speeding up, it's not slowing down. The speed is remaining constant. So when we talk about speeding up and slowing down, we're talking about acceleration. So in the next graph, we're going to describe the acceleration. Versus time. So the formula would be acceleration at equals what? So we look at the speed graph and we notice that the speed of the animal is not speeding up and it's not slowing down, it's remaining constant. So what that means, acceleration is the change in velocity or speed. So the acceleration is actually 0. So we draw a line along the x-axis and we say AT equals 0. So what we've done here is we've basically described the slope of the first graph, the relationship between distance and time, and that the slope that we described was described in the next graph. So that is actually speed. And then for the speed graph, we describe the slope of what's happening, the rate of change for the relationship between speed and time, and that's described in the acceleration graph. So what we've done, because we know that slope is the same thing as the derivative, is we've actually taken two derivatives. So that's how simple derivatives are. Derivatives are simply, you're simply finding the rate of change. In fact, that's so important, I'm going to write at the top. It's rate of change. Another way of saying is the slope. So these graphs are pretty straightforward, but when derivatives really shine is when you're actually working with curved lines. So let's look at that now. So let's continue with our biologist example. So our biologist is in the field, and this time they're studying an animal that's moving rapidly, hunting another animal. So what we're going to do is we're going to draw 3 graphs to do a comparison. As I said, we have an animal that's moving slowly in the beginning, stalking the animal, and then moving faster and faster. So is the relationship between distance and time. And the graph would look something like this. So as the units of time increase, the change in the distances becomes greater. So this line becomes steeper. So our formula for describing this would be distance dt equals t squared. In other words, it is moving faster and faster over time. So in the next graph, we're going to describe what's happening in the first graph. So we will call this velocity, which is the same thing as speed, just has direction. So how will we draw that? We will draw a straight line that is increasing, but notice the rate. So write v t equals 2t. So notice that it is not at the rate, that's the change is actually changing at the rate of 2t. And then the next graph we're going to describe what's happening in the velocity graph. So the y-axis will be acceleration versus time. So how is this accelerating? What do we notice about it? It's actually a linear relationship. It is accelerating at a constant rate. So the acceleration is actually constant. So we would draw a horizontal line like that. And we would write our formula. So the acceleration over time, or AT, equals, so how is it accelerating? What is the relationship? It's actually remaining at 2. So the acceleration over time equals 2, or a constant. So notice that when we go from the distance to velocity, velocity is actually we're finding the derivative of distance. We've determined what is the formula for the slope of distance versus time, and that is 2t. So 2t is the derivative of the first graph. And then in the acceleration graph, we've actually figured out what is the derivative of the velocity versus time, and the slope or the derivative of velocity over time is 2. So that is a little bit about the meaning of derivatives, and I just want you to go away with the idea that derivatives are not super complex. We're simply dealing with the slope of a function. Thank you.